radiation, that is to say, the creation of electromagnetic radiation, electromagnetic waves, if we had some prescribed sources that were changing the function of time. For example, we have some antenna that's oscillating current and will then radiate. Okay? A related and important problem that I want to finish up this discussion with is a very short discussion about, meaning today and maybe part of Thursday, scattering of electromagnetic waves. So of course, the scattering of waves is a very involved subject. We can spend weeks upon weeks doing this. We will. We just want to highlight some important features that give us some of the key concepts. Okay? So what we're talking about here is thinking about a situation, the standard paradigm, where we have some object that we call the scatterer, which a piece of glass, maybe it's, dust in the galaxy, whatever it is that's going to be scattering electromagnetic waves. We're looking at some localized scatterer. We have some incident wave, which we'll think about as a plane wave with some incident wave vector. And then we are going to look at the wave that is detected very far away from the scatterer, asymptotically far away. Imagine that we have some pinhole, which then defines some direction, and some detector over here, which thus defines some scattered direction, some scattered wave vector. Okay? So we have the incident wave and the scattered wave. And as you know, the way in which we traditionally try to characterize this process is by thinking about the scatterer as presenting an effective scattering cross-section to the incident wave. And so that's typically the key quantity that one calculates in the context of scattering, is the scattering cross-section. Okay? And just to remind you, I know many of you are studying this now, reminding yourselves about this in quantum mechanics, but let me just remind you again what the notion of cross-section, how that comes about. When we talk about a cross-section, a scattering cross-section, the way that this is defined is whether, regardless of what we're talking about, whether it's electromagnetic waves or particles or what have you, the scattering cross-section is defined by thinking about the rate at which stuff is scattered divided by the rate of incidence of stuff per unit area. That's the definition of the scattering cross-section. So that when you multiply this by the area, the cross-sectional area, so this says units of area, then you get the rate at which stuff is scattered. Okay? So what is the stuff that's being scattered here? It's electromagnetic energy. Okay? So in this case, for electromagnetic waves, the scattering cross-section is defined to be the power scattered divided by the incident intensity. Okay. Then it has the units of an area. You multiply the incident energy by the cross-section, the scattered cross-section, you get this power scattered. Okay? Now, there's lots of little labels we can put on this depending upon exactly what we're talking about. Quite often, what we're interested in is a differential scattering cross-section. Okay, so we might be interested in per unit solid angle for a particular scattering direction, how much power is scattered into that direction, differentiate. So then instead of thinking about the total scattered power, we would talk about the differential power scattered per unit solid angle. Just like we've talked about in the last few lectures, we talked about the differential power radiated per unit solid angle. So the differential scattering cross-section per unit solid angle, given a certain incident direction, or incident wave vector and scattered wave vector here, would be equal to the differential power scattered into that wave vector divided by the incident intensity in that wave vector.
I mean, the answer to that is yes.
Okay.
But, how would the thing?
Now, there's a little bit even further complication to this, which is, of course, the waves themselves are vector waves, and we have two degrees of freedom, or two possible polarization states, right? So we could say, which could be some superposition of polarization in this plane or perpendicular to this plane. It could be circular, who knows? But there is some incident wave vector, and we may be interested in how much power is scattered into a particular polarization state, or not. We may not care about that polarization state, but we, for the moment, we'll keep track of it, so there could be scatter in the same plane or perpendicular to that plane. So really, I should stick in here an incident polarization vector and a scattered polarization vector. Okay? All right, so now we're going to restrict our attention here to the case where we're looking at a localized scatterer, which has some size d. And we'll think about, for the moment, long wavelength scattering. Where the wavelength of light that we're talking about that's coming in here and is being scattered is huge compared to the size of whatever it is that's doing the scattering. Okay, so maybe this is a molecule and we're sending in UV light or maybe infrared light. Regardless, that's still big compared to angstrom size. We're talking about, say, X-ray scattering at the moment. Okay? So, when that's true, what we've been studying in the last few lectures, we know that whatever, so what's going to happen? What's physically going on when the scattering is happening? What's going on is the incident field comes in and starts to drive forces on the charges that are generally bound, and they will oscillate as they're being forced, and they will re-radiate. That is what's going on in the scattering process. Okay? Now, of course, there's a more self-consistent problem because the fields that are created can also affect other parts, and there's a whole self-consistent solution. But to lowest order, we can think about this as the incident field comes in and it drives some currents, and those currents re-radiate. And that re-radiated field is the scattered light. Now you just solved a problem like that in homework in 1D, right? Where you had a plane wave came in and it shook the surface current and that re-radiated, and that re-radiated field radiated only, you know, forward or backward because it was a one-dimensional problem, and that corresponded to scatter in 1D. Okay, but now we're in many D, maybe 2, 3, won't be in that. Okay, so given this notion of the incident field drives current that re-radiates, and thus this is the scattered field.
Doesn't that assume total absorption by the...
No, it does not. It's what, as we'll see in a moment and remind ourselves, the amount of the field that is absorbed depends on the response of the medium. Okay? We'll get to that in a moment. Remind ourselves about that. Okay, but given this is true, or said another way, C over omega is much less, or much greater than D, or omega is much less than D over C over D. Okay. Then we know from our studies that we just did that under this circumstance, the fields that are radiated by these oscillating sources are dominated by the lowest non-vanishing multipole moment associated with that distribution. So in the long wavelength limit, when the wavelength of the field is big compared to the size of the source, then we know we can do a multipole expansion, as we have studied for the last few lectures. And the electric dipole radiation dominates. Unless for some reason or another, the source, the electric dipole moment, vanishes by some symmetry, right? Like, for example, if I am looking at near resonance scattering of an atom by some kind of, say, laser beam, and I'm driving that near a transition, which is electric dipole forbidden, because of parity selection rules, then the electric dipole will be 0. And then I might have to think about higher multipole moments. But in general, you know, there will, unless there's some very special symmetry that forbids the electric dipole moment will dominate. Okay? So what that means is that if I put the origin right at the center of the scatterer, then we know what the scattered field will be. The scattered field well, it will just be the induced dipole moment will radiate electric dipole radiation at the frequency of the incident wave, assuming I'm driving at that frequency. Okay, so that's the complex amplitude, even minus I omega t. All right? That's electric dipole radiation. All right, so now we can calculate the differential scattering cross-section, assuming we send in a plane wave with some polarization. And we want to know what is the scattering cross-section, differential scattering cross-section into a particular direction with a particular scattered polarization. All right. Let's see, what do we have? Well, we need to know what is the differential scattering cross-section. I mean, the differential power scattered. Well, that's the power radiated by this induced dipole moment into that direction with that polarization divided by the incident intensity with that polarization and that wave vector. Okay. But this is what we've calculated, generally speaking. This was equal to, regardless of the radiation, this is r squared d omega into the direction k dotted into the intensity. This is the scattered intensity. So this is the Poynting vector associated with the scattered wave. This is through that solid angle into the direction k hat per unit d omega. So that's dp radiated, or I say scatter, called radiated, same stuff, over the incident intensity, which is k incident dotted into the incident Poynting vector. So this is my incident intensity, and this is the amount of intensity through that little area per unit solid angle. We're a little clear on that. So this then is equal to r squared this is going off, the pointing vector is being radiated, or where is that? There it is. The pointing vector is being radiated into the direction of k. This is equal to k scattered dot r, where k scattered is k r hat, so that's into the r hat direction, so that's all good. And then the magnitude of this is c over 4 pi, the magnitude of the electric field in the scattered polarization. And that gets divided by k incident. Well, this is in the k direction. This is c over 8 pi. The incident polarization dotted into the incident field squared. So this is equal to r squared, the ratio of that electric field squared over the incident amplitude squared. Alrighty. But we know what the scattered field is. So we can plug that in. We multiply this, we square it. The r squareds canceled, as they must. And then we get a k to the 4. So we have a k to the 4th. The dot product between the scattered polarization unit vector dotted into the transverse component of the induced dipole moment squared divided by the incident amplitude squared. All right? So now, right now, the only assumption we've made is that whatever fields are being generated in this process, there is some induced dipole moment that is oscillating at the frequency associated with the incident wave. And that oscillating dipole radiates. That's what we've assumed. Okay, now we're going to make further simplifications. The first thing we're going to do is we're going to make what's known as the firstborn approximation. Which is equivalent to saying we're going to neglect multiple scattering. So this is an approximation that the amount of scattering is weak. And in that assumption here, then we can just say that P induced is due only to the incident field. We're ignoring any re-radiated effects that affect the dipole, any back action effects. Okay? So if we wanted to solve the full scattering problem, we'd have to include that. That's known as the firstborn approximation. There, of course, as you know from your quantum mechanical studies, there's a whole power series that we could derive in terms of to include the effects of multiple scattering. Okay, so that's the first thing we're going to do. The other thing we're going to do is we're going to assume a linear response. Of the scatterer. So that our induced dipole moment will just be what we've studied when we looked at material response, there's some polarizability at whatever frequency times the incident field at the position of the scatterer. Okay? Alpha is the polarizability. So that's what we've studied, and you're going to be studying a lot for your exam. And so now we can use this assumption to see what the scattering cross-section is under this assumption. Okay? So this implies that the differential scattering cross-section given in the incident field with that polarization and that wave vector scattered into that polarization with that wave vector is equal to k to the fourth, the magnitude of the polarizability squared, the perpendicular component of the incident field squared divided by the incident field along whatever direction we care. That's what we got from that expression. Okay? Does this have the right units? Well, this is dimensionless, so that's cool. What are the units of the differential scattering cross-section?
Area?
Area, right? Length squared, because the solid angle has no units. Sigma is an area. What's the unit of K? 1 over length. So this is 1 over length of the fourth. So the whole question is, what the heck is the unit of alpha? But you remember that alpha, as we discussed, has units of volume. Okay? So this is length cubed, length to the sixth, over length to the fourth, length squared. That's right. At least that part's right. It might be factors of 2, whatever, but kind of all you need to know. Numerology tells you a lot. Okay. So now we have to ask the question of, okay, we have now a dependence of this cross-section. Of course, we're going to look at this for specific cases of what alpha is for some model of our scatterer. But I want to take a look at the moment at this dependence on polarization. Okay? So, so we have some incident wave vector, we have our scatterer, we have some scattered wave vector, okay? And we define, in this case, theta as the angle of scattering relative to the incident direction. Okay, so now, as you know, there are two natural polarization states that we can consider for this incident wave. The two wave vectors define what's called the plane of incidence. So the plane of the blackboard is the plane that I've drawn that includes the two vectors, the incident wave vector and the scattered wave vector. Okay? And so there is a polarization state in the plane of incidence, which is parallel. So it's called p polarization or pi polarization. and polarization state perpendicular to the plane of incidence. And because this was done in Germany, it's the German perpendicular, which is something that starts with S. That I don't remember. It's like train conf. I don't know. Where's our Würzburg students? But since perpendicular starts with S, it's called S polarization. Okay? Which, not to be confused with the scattered polarization, this is all called the sigma. So there's pi and sigma having to do with whether or not the polarization is parallel or perpendicular to the plane of incidence. Okay? Now we can ask, given a certain polarization state, how much scattered light is there into all polarizations? Okay? So what we want to know is the differential scatter and cross-section, say, given sigma polarization, I'll call it sigma so we don't get confused. Of course, there's only one, if it's polarized, assuming in this case that my polarizability is a scalar, then the direction I can't couple pi and sigma. If I had a vector or tensor thing, I can couple one polarization state to another. But here, it's a scalar. So if I put in sigma polarization, then the output is sigma polarization. Is that clear? Okay. So I don't have to write it again. What is P perp in this case? Well, it's all of it. All of it is perpendicular. For if I start with oscillation in this direction, no matter what theta is, because in the plane of incidence, the whole component is perpendicular. Okay? Of course, the whole thing is azimuthally symmetric. In this case, P perp is the whole P. So in this case, we have, okay, so just to draw the picture again, we put in light, here's the incident wave vector, here's the incident polarization perpendicular to the plane, here's my scatterer, it radiates a spherical wave that's coming out of the board isotropically with respect to this axis. And so independent of theta. Okay, for pi polarization, on the other hand, we know that that's not true. In that case, maybe I should draw that on a different board so we can see it better. So this differential scatter and cross section, I have pi polarization. So now I have to think about what component of the pi polarization is perpendicular. Let's take a look. Remind ourselves, in this case, we're starting with polarization like this, and the scattered polarization has to be transverse. if this is my angle theta, the component that is perpendicular is equal to this component cosine theta. So this then, in this case, is k to the 4th alpha squared cosine theta squared. All right, so what this furthermore says is that if we start incident light is unpolarized, has incoherent mixture of sigma and pi polarization. Well, so let's say I came in with light and had equal amounts of intensity with no interference between them, between pi and sigma. And here's my scatterer, and now I look in different directions. Well, the degree of polarization will depend on the angle in which I look. If I look in this direction, I see complete perfect polarization. In fact, the only light that can be scattered in this direction is sigma polarization, because the pi polarization cannot be transverse. Whereas if I look in this direction, I see completely unpolarized light. I see equal amounts of pi and sigma, because in this direction, it's all perfectly transverse. And as I look in different directions, I see less and less and less of the pi, but the same amount of sigma. Standard optics factoid. All right. So if we were interested in, if on the other hand we were interested in what is the total amount of light scattered independent of polarization, so here we have the differential scattering cross-section for unpolarized light into all polarizations, then the sigma d omega is then the average of these two. Half of it is the amount that's pi, and half of it's the amount that's sigma. That's just the average of these two. Half of the intensity comes in as sigma, and half of it comes in as pi. So we just average them. All right. So now let's talk about what should we take for alpha. Let's consider a Lorentz oscillator model of a molecule that scatters. So we have discussed this. If we assume, let's assume we have a single resonance that we're going to care about, then our polarizability takes the form if the signs randomness, you get mad, but you just get there. So this is the case where we have a resonance at frequency omega naught with damping. Yeah. So the nature of the scattering that happens depends substantially on how the frequency of the incident light, which drives this oscillation, how close it is to resonance and where it is relative to resonance. Okay? So the first case we'll consider is suppose the frequency of the incident light, which drives this oscillating dipole, is huge compared to omega naught. Okay? This is the case where that it looks like almost looks like a free electron. Of course, omega naught we assume to be huge compared to gamma. So under that circumstance, this thing is approximately minus e squared over m omega squared. Under that assumption. All right, so then we can take a look now at our differential scattering cross-section for unpolarized light into all polarization states. That's omega over c to the fourth, e squared over m omega squared squared times 1 plus cosine squared theta over 2, where theta is the direction between the incident and scattered wave vectors.
One half.
Oh, yeah. That's, all right. So for this case, the frequency dependence cancels. And we see that if omega is huge compared to omega naught, then my differential scattering cross-section takes the form e squared over mc squared squared 1 plus cosine squared theta over 2, which is equal to something we call the classical electron radius squared over 2. So the classical electron radius is defined as the ratio of e squared divided by the rest mass of the electron. Remember, why is this called the classical electron radius? Well, but why is this why is this ratio what you might consider to be the radius of the electron classically? The Bohr radius has h bar in it. So there's no h bar. I mean, what this says is that mc squared is e squared over rc. So classically, you can imagine, or you might have one model to say that the rest mass is arising from the potential energy of the charge, E, all smushed into that radius. Okay? Well, it's a scale that comes out when you have E, M, and C. This radius, of course, it's not the radius of the electron. At least we don't know what the electron radius is. Maybe the string theory will tell us, but for the moment, consider them to be points. But this is a number that comes out in this, and this number is equal to 2.8 times 10 to the minus 13 centimeters squared. Okay. So,
Is that the radius?
no, I'm sorry, the times, this is just the radius. Okay. So now we can ask, what is the total cross-section? And so we need to, that's called the Thomson scattering cross-section. So that's this thing integrated over all solid angles. So it's independent of phi. I can write this as 2 pi d cos theta. That's the element solid angle integrating over all the phi. So then that's equal to the cross electron radius squared over 2, the integral, I'll call this mu goes from -1 to 1, 1 plus mu squared over 2, which is 2 pi. And I already got the half. So that is equal to 8 pi over 3, the classical electron radius squared. That's the Thomson scattering cross-section, which is equal to 0.665 times 10 to the minus 24 centimeters squared, also known as 0.655 barns. Okay, now a barn, somebody had a joke and decided that, you know, how big is a uranium nucleus? Well, it's as big as the side of a barn. And that's stuck as the unit of cross-section in subatomic physics.
Is that really?
That is true. That is true, that's correct. All right, now one thing to note, of course, there's many, I say this is big compared to omega naught, but it still has to be sufficiently small that the multiple expansion still works. Moreover, note when the energy of the photon as associated with it in quantum mechanics is on the order of the rest mass of the electron, this whole thing falls apart. The wave nature of the light is replaced by the particle nature of the light. And that is what we call Compton scattering. So if we start talking about, gamma rays or hard X-rays, then this falls apart. Okay, but if we're talking about UV or something like that above some resonance, then the Thomson cross-section is the relative one, thinking about scattering through a plasma, for example. All right. Let's now look at the other regime. Let's consider the case where the driving frequency is very, very small compared to the resonance frequency. Okay? This is what we call Rayleigh scattering. So in that context, my polarizability is approximately E squared over m omega naught squared. Okay, also I'm going to assume that omega is small compared to. So under this circumstance, well, that's not really important as long as we're looking at it far from resonance. This will be the dominant effect. Then my differential scattering cross section, well, has exactly the same form that we have over here, except it is scaled for the Rayleigh scattering by a factor of omega over omega naught to the fourth power times the Thomson differential scattering cross section. Right? I mean, if we look at it over here, the only thing that we have is that we're getting rid of that omega to the fourth power, and replacing it by omega naught. So the total Rayleigh scattering as a function of frequency is equal to the frequency over the resonance frequency to the fourth power times the Thomson scattering cross section. Right. So, well, of course, this explains why the sky is blue. Right? Let's remind ourselves of that. I've never seen that before. Well, firstly, if we're talking about the atmosphere, the dominant scatterer is nitrogen molecules. Okay. And the resonance, the dominant resonance, is at a wavelength of about 75 nanometers. What kind of electromagnetic radiation is that at 75 nanometers?
X-ray.
It's ultraviolet. So this is a RUV, far UV. So if we're talking about visible, this is the resonance wavelength, between 400 and say 600 nanometers approximately. So the frequency of light is much, much lower than the resonance frequency of the scatterer, which means that Rayleigh scattering is what's dominating the scattering of visible light from the atmosphere, which means that the scattering is much, much stronger for the shorter wavelengths than for the longer wavelengths, which means that if here's the atmosphere and here's me, you recognize me. That's how you recognize me. Here's the sun. Sun's smiling, I'm not. then if I'm looking over here, what I see is the light that is scattered to me. Okay, it's not coming directly to me. And this light is bluish, because the lower wavelengths are scattered less. And you might say, why don't I see purple sky? Because purple scatters more than blue. That would be pretty. Why don't we see a purple sky?
Our eyes can't see it very well.
Because what?
Our eyes can't see it very well.
That's right. So we have to convolve what the light is with the response function of our eyes, and our eyes see better towards the green or yellow than they do towards the higher frequencies. Okay, so there's a response of our eyes as well, because there's a lot more light at the peak of the black body spectrum of that. Okay. Now, of course, when the sun starts going down, and here I am, my lovely little townhouse, my bottle of beer or something. And I'm looking, what I see when I look at the sun, what I see is light that looks redder. Why?
So blue light gets figured out.
Because the blue light has mostly been, the bluer light has been scattered away. Now, why doesn't the sky look, if I look at the sun over here, why, when I'm at noon versus sunset, why doesn't the sun look as red at noon than it does at sunset?
Because it's going through less.
Is going through less of it. So the question that we need to address is, what's the characteristic length of attenuation of the light by scattering? And how does that compare to the thickness of the atmosphere? So this length, if this is the length that it goes through at noon, and this is the length that it goes through when this is, say, at 5 degrees, then it must be the case that there is substantial, much more substantial attenuation of the light by scattering at sunset than there is at noon. So let's conclude our lecture by studying that. Yes?
What about on the left diagram when it's at noon? You know, if I squint really hard at the sun, I'm pretty sure I'll still see blue sort of around it.
You mean, I mean, there's a whole much more of multiple scattering. So almost all the light you're seeing is scattered light, except the light that, I mean, the sun itself doesn't look blue.
No.
So it's white, right? But everything around it is almost all scattered light. It's not coming directly to you because there's sufficient multiple scattering.
So like some kind of albedo, just a bunch of reflected scattering.
Well, the light that's here coming, some that comes in here can be, scattered multiple times before it comes to you. All right, so we're going to ignore that fact and just talk about the firstborn approximation. Okay, so let's talk about attenuation by scatter. So what I mean by this is, let's say I have some laser beam or beam of light that traverses some cell of scatterers. Okay? So there's some incident intensity and some out intensity. And I want to know how the intensity varies as a function of distance that I propagate through this cell of atmosphere. Okay? So we can derive, very simply, a differential equation that describes how the intensity varies as a function of distance z. By just looking at a little differential slab of the stuff, some thickness z, dz, and here I have I with z, here's I at z plus dz. Okay? So, the change in the power is equal to minus the power scattered traversing z to z plus. Okay. The power has decreased because power has been scattered. Okay. So what is this? Well, this is di times, let's call the area A of this D. And the power scattered is what? Well, that's what we just said. That's equal to, for each scatterer, the powered scatter is the intensity times the cross-section. That's the scattered power. So we just defined as a scattered cross-section. But inside this little volume, there are n scatterers. Scatterer. Okay? And the number of scatterers is equal to the volume of that little disk times the density of scatterers, which I'll call little n.
You could find a much better operator procedure.
So this then is equal to minus A, the density, the cross-section, I, dz. Or di dz is equal to minus the density times the scattering cross-section times I. Which has the lovely name of Beer's law. It's not what I'm doing when I'm drinking a beer watching the sunset. Beer was a guy. Maybe he was a guy, maybe she was a gal. I don't know. But someone named Beer had a law, and this is their law. All right. So Beer's law is pretty simple. It says that under this assumption, on the assumption of no multiple scattering, we get an exponential decay in the intensity due to scattering. It says that the intensity as a function of distance propagated is e to the minus n sigma z times the intensity at the input phase. Okay? So n, the density times sigma, is equal to 1 over some, I'll call it A. A is the attenuation length. also known as the mean free path for scattering. So if I have a total, if L is the length of propagation, then n sigma times L is known as the OD, the optical depth. Also sometimes known as the optical density, even though it's not a density. The OD. So, if the total amount of intensity that gets attenuated depends on the OD at the frequency of interest. All right, so now we want to know what is the OD for scattering of, say, blue light through the atmosphere at noon versus at sunset. All right, so now we need some numbers. Got to look at my handy notes here. Let's see what we need. That's right. Atmosphere. At noon, the density of nitrogen molecules times the thickness of the part of the atmosphere that we care about is approximately equal to 1.7 times 10 to the minus 25 per centimeter squared. All right. So, for blue light, say at lambda equals 450 nanometers, using that formula over there, where we have the resonance frequency at 75 nanometers, that gives me the Rayleigh scattering cross-section is equal to 2.17 approximately times 10 to the minus 16 centimeters squared. Okay, so the fraction of blue light scattered at noon through this length, which is 1 minus the Beer's attenuation, is 8.6 times 10 to the minus 3. Fraction of blue light scattered at sunset. So now we need to know what is L prime. Let's look at this picture here and just assume, let's say sunset is at, when we're setting at 5 degrees over here. So let's see what is L prime. So this then, L prime is equal to L divided by cosine of 5 degrees, which is about 11.5 L. So we're about, about an order of magnitude thicker at sunset than at noon, when say sunset's at 5 degrees. So we plug that in and we get about 10% scattering. Okay. So the bottom line of it, of course, is that the mean free path for scattering blue light is sufficiently large that at sunset, a substantial fraction of the blue light is scattered by attenuation, and we have beautiful pink and red sunsets. All right. All right, we'll conclude our discussion of scattering next time.